It's odd now.
Can I bother you to say something so that I can check the mic?
Hello? Can you hear me?
Sounds good. Thank you.
Maybe a little bit bigger.
Bigger?
font size.
You think so?
Yeah, when you're here, it looks big, but when you're back there, it may look a little small. So a little bigger. Start the intro. All right. Well, it is always a pleasure for me to introduce the guy whose dorm room was across the hallway from mine during TASI all those years ago, John McGreevy from San Diego. John was trained as a string theorist, but a lot of what he does now is in condensed matter, and he's going to be telling us about generalized symmetries in condensed matter theory. John.
Thank you, Oliver. Okay, I'm very happy to be back. Can everybody hear me? That's good. Not very well. Okay. Let's see. Is that better? No? Should I speak up maybe? Will that help?
I can hear that the mic is on.
Okay. All right. So so my title is Symmetries in Quantum Matter. This is a more refined title, Generalized and Emergent. And my rough plan is the following. We've already had at the school a number of beautiful lectures about describing gapped phases of matter using topological field theory. So I feel like maybe it's my job to give more of a condensed matter-y point of view on some of these ideas, and maybe back up a little bit and say something about a big picture of how we think about phases of matter. I'll say something about this. So there's this thing called the Landau paradigm, which is the idea that we should understand distinguish phases of matter by how they represent their symmetries, more specifically by what symmetries they break spontaneously. And if you've been to a condensed matter talk in the last 20 years or so, you've seen the kind of beating that Landau's been taking for saying this. The speaker begins by saying, Landau, that dummy told us that we're supposed to classify our phases of matter by what symmetries they break. But in this talk, I'm going to tell you about a phase of matter that's distinguished by something else. And then they draw a picture of a donut, usually. By some kind of topology. So after saying a little bit about these phases, these so-called beyond Landau phases, I want to explain how, if we're willing to generalize a little bit what we mean by symmetries, and I think all of you are willing to do that by now, and if we're also willing to generalize a little bit what we mean by Landau paradigm, we can actually understand many of these so-called beyond Landau phases in terms of how they represent their symmetries. Okay, so that's the first two goals, and then I'm going to start again from a somewhat more austere point of view, which is called entanglement bootstrap, which takes a little bit of introduction. But my purpose of introducing it is that it gives another way to understand generalized symmetries in quantum matter, which I think is quite nice. It's sort of and moreover, it gives a way to understand why topological field theory should be a good description of certain gap phases of matter. So topological field theory, as you may have noticed, is a very nice thing, but it requires some assumptions, right? It's, people prove things about topological field theory, but those are mathematical statements that start from some set of axioms and then arrive at some conclusion. And it's not entirely clear that those axioms that were chosen by mathematicians are the right ones. Maybe they are. I don't want to disagree. And in 2 + 1 dimensions, I'm pretty sure they are. But especially when we get to higher dimensions, it's much less clear that all of these assumptions are the right ones. And so it's very nice, I think, to have a starting point that, the starting point here will be, we'll just start with a single quantum state, or which we'll take as sort of representative of a phase of matter about which we'll make some reasonable assumptions, and then we'll try to extract all of the universal data from it. So that's the idea of entanglement bootstrap, from which we can, so we'll see topological field theory and generalized symmetries come from that. And then at the end, hopefully we'll have time, I want to say something about using the same point of view to understand the emergence of conformal symmetries. That is, it's a generalization of this perspective, not just to gap states, but to conformal field theories in 1+1 dimensions, and to chiral states in 2+1 dimensions with gapless boundaries. Okay, so that's my goal. Was there a question? Yeah, any questions? Okay, so so let's get started. Oliver says I should write a little bigger than this. Okay, so what is the Landau paradigm? Probably there's some disagreement about this. Yeah, that's my font. I don't know what to say. Yeah, Apple Plus. Okay. Let's see. I'll try. So what does it say? One thing it says. The board space is so valuable. Okay. Right. It says phases of matter should be labeled by symmetries, by, let's say, by how they represent their symmetries. And I'm saying it in kind of a weaselly way because I want it to fit what I'm going to say later. The less weaselly way to say it, which would be wrong, is by label them by what symmetries they break spontaneously. A sort of second aspect of this, a second belief that comes along with this point of view, is that light degrees of freedom, so I mean degrees of freedom excitations whose energy is less than some, say, intrinsic mass scale, microscopic mass scale, or degeneracy, if we have some degenerate ground states, say, they should arise because of the symmetry. They should be swept out by symmetries. So that is, they should be something like Goldstone modes. And I guess the third part, which maybe I can write small because I'm not going to talk about it too much, which is about what happens at critical points between phases, is that the critical degrees of freedom should be fluctuations of the order parameter. So a phase of matter breaks a symmetry, there's some, well, in the old-fashioned story, there's some local operator that's charged into the symmetry and has an expectation value, that's the order parameter, and they should be, the critical degrees of freedom are the fluctuations of the order parameter. I think that's probably a fair characterization of what Landau said, and of how it's been used in condensed matter physics to understand basically everything most everything we understand about condensed matter physics. I guess maybe this is an important thing to emphasize. Like if you go to the March meeting of the condensed matter meeting, like nearly all of it is not about interesting topological phases. The most useful tool is this thing I'm about to say. Okay, so this is beyond its conceptual utility. It's these statements really are they can be weaponized and lead to this tool that's used all the time, which is I guess it's sometimes called Landau-Ginzburg theory or Landau-Ginzburg-Wilson-Fisher theory, depending on who you talk to. And maybe it's worth spending a few minutes reviewing how we get from these statements to that useful tool. Landau-Ginzburg, Wilson-Fisher, and it's a application of effective field theory. It's just combining the ideas of effective field theory with these three sentences that I just said, and recall that effective field theory is something that something that you can do by filling out a survey. And here's the survey has 3 questions. The first question is, what are the symmetries? Oh, I'm writing small again. What are the symmetries? The second question is, what are the degrees of freedom? And the third question is, what is the cutoff? And if you answer these 3 questions, Ken Wilson will tell you what your Lagrangian is. And the idea is that using these 3 principles, we can answer these 3 questions. So I guess, okay, we can't answer the first question. So there's somebody has to tell you what the symmetries are. Somehow you know what the symmetries are. Let's say, okay, here's my, so 0 is what is your name? Right. Right. Okay, so my name is John. My symmetry is U1. And so, okay, what are the degrees of freedom? For this one, we get the answer from Landau. So degrees of freedom should be swept up by the symmetries. The degrees of freedom should be some local operator that's charged under the symmetry. It's something that it's local, and it's a representation of the symmetry. So it transforms linearly under the symmetry. Okay, and well, where do we get such a local operator? Well, the idea is that this is an effective field theory for whatever thing we're trying to describe that has a U1 symmetry, and this operator is some coarse-grained thing. It's not a microscopic degree of freedom, but rather it's some like in a magnet, it's some magnetization averaged over some region of space. It's some coarse-grained thing, and the cutoff is that length scale over which we coarse grain. So I don't know. This is some coarse graining length scale. Okay, and then so this then Ken Wilson turns the crank, and out comes a Lagrangian, which it's a function of functional of your degrees of freedom, and it's symmetric, it's local, meaning it's a single integral over space-time. And we can organize it in a derivative expansion. So that is, we can organize it from most relevant operators to least relevant operators. I guess the most relevant thing we can write down is something like phi squared. All the terms have to be individually symmetric. Let's call this R. And then we can add some derivative terms. And then we can add some dots, some terms that aren't going to matter. Okay, and I guess I should write absolute value since I wrote a U1 symmetry. Okay, so just from this input, we learn that, well, the potential either looks like this, if R is positive, or it looks like this, if R is negative. In this case, the symmetry is not broken. In this case, the symmetry is broken. So it reduces the problem to a collection of, some collection of coefficients for any resolution of an experiment that you want to explain. Only a finite number of them matter, and determining those coefficients says what happens. Okay, so I hope you can appreciate why people like this story so much. Right? Just from very little input, it gives very strong constraints on what should happen. Okay. And it works. Yeah, that's right. That's right. Well, okay. So good. Exactly. So thank you for that transition, because so maybe there's some times when it doesn't work, right? So that's exactly what's at issue. So are there phases of matter that are distinguished by something else, right? That's what you might call not working. Well, there's a list of them. Maybe I won't write the list now. So I guess briefly. There are things like topological phases, which are distinguished by donuts, but are distinguished by something other than symmetry breaking. There's Landau's own Fermi liquid theory, which is distinguished from something else by its Fermi surface worth of gapless degrees of freedom. There's there's things like Coulomb phases. So I guess one example of a Coulomb phase is the phase of QED that by which we're seeing each other. But such phases can also occur in materials. They're generally something like a gapless spin liquid is something where a photon can emerge as a low energy degree of freedom in a phase. Okay, so there's a few other examples about which I'll say a little more later. Okay, so maybe let me begin with, I guess now we're up to section 1. Let me start with this is section 1. Let's think about what do we mean by phases of matter a little bit. Okay, so the most basic distinction that we should make is whether there's a gap or not, right? So let's call a state is gapped if the spectrum of the Hamiltonian in the thermodynamic limit looks like this. Okay, so this is as L goes to infinity. So I'm using L as a name for my system size. So if in the thermodynamic limit there's a separation between some number of ground states, I'm not demanding that it's just a unique ground state, some number of ground states and excited states, then we'll call it gapped. And I guess I'm also going to demand that these degenerate ground states are that this degeneracy is robust. So what I mean by robust here. You're saying the state is gapped or like the phase is gapped? Yeah, let's say the Hamiltonian. Yeah, good, thank you. Hamiltonian is gapped. And if this is true, that's the spectrum of the Hamiltonian. I'm really all I'm emphasizing is the thermodynamic limit. And then I don't really care about these excited states today. Really, this is a property of the ground state, the property of the collection of ground states. And yeah, but you're right, Oliver. Thank you. I do want to be saying something about a phase. And so let's so this is the second part of the definition. Let's call a gapped phase. A gapped phase is an equivalence class of such Hamiltonian. An equivalence class of Hamiltonians or their ground states, where we regard two Hamiltonians as equivalent if we can get from one to the other without closing the gap. I have more to say about the definition, but yes, please.
Do you consider non-local Hamiltonians?
No, I don't.
What was the question?
The question was, do I consider non-local Hamiltonians? And yeah, I really want to think about local Hamiltonians. Yeah, let's talk about local Hamiltonians today. Yeah, I could probably get in trouble if we allow non-local Hamiltonians. Okay, yeah, good, thank you. And so the picture we should have in mind is, so now I'm going to draw a really scary picture. It's a picture of the space of Hamiltonians, and indeed I really do mean local Hamiltonians. And to really make sense of this, we probably have to make some other assumptions about it. And so here's a point in the space of Hamiltonians. And let's assume that this is a point where there's a gap, and this is another point where there's a gap. And then there's this really scary thing, which is the wall of gap closing, which I'll draw in red here. Yeah, this is the wall of gap closing, where it doesn't look like this, where instead the spectrum is, there's states everywhere. And then here's some other thing B, which is separated from A and A prime by the wall of gap closing. Okay, so now I guess maybe one thing I should say is what a little bit more about what I mean by this space. So one way to get from here to here is just by adiabatic continuation. Just vary the parameters. And if I can vary the parameters from here to here without closing the gap, we say they're the same. Another thing you can do, though, is you can also add decoupled bits. Right? So if I have some Hilbert space of, say, spins on some lattice, I have some Hamiltonian with a gap. If by adding in some extra degrees of freedom and including them in the interactions with the degrees of freedom I have already, I can get to some other Hamiltonian, then I also regard them as equivalent. So this path is, it's a slightly scary thing. It's not just adiabatic deformations, it's also, I can also change the microscopic Hilbert space. Okay, right, and so we call those the same. So now there's one very obvious problem. Yeah?
Is it obvious that if you think that things are separated by a gap, a wall of gap closing here, that there isn't some crazy degree of freedom you can add?
Wonderful. So Oliver has anticipated exactly what I was going to say next, which is, I drew this line, and how do I know that I can't go around it? Right? How do I know that, this is a very high dimensional space? How do I know there isn't some path? to get from A to B. So exactly because of this problem, exactly because it's really annoying to have to study every possible path from A to B to prove that they're in different phases, wouldn't it be nice if there was some way to tell, given two Hamiltonians, that they had to be in different phases? If there were, say, some invariant, some kind of quantity that is the same for every Hamiltonian in the same phase and different for Hamiltonians in different phases. So that second thing is maybe a little harder, but imagine that there's some integer you can attach to every Hamiltonian in this phase that's the same, right? And the nice thing about an integer is that it's something that can't vary under smooth deformations, right? It can only change by jumping. For example, it could change if the gap closes. So there would be one integer here, and just by comparing those integers, you could tell that they're different phases. Yes, please. Yes. Right. So that's the question. Yeah, the question was whether we can define phase. Yeah, saying yes 5 times is probably less useful than repeating the question. Yeah. Okay. So the question is whether this is a property of the ground state, or whether we really need to have the whole Hamiltonian to define phase. And indeed, I personally strongly believe that the phase is a property of a single wave function, and I'm going to spend the last three and four are entirely about that principle. But it's a little harder to give the definition from that point of view. Yeah, so I'm being cowardly and introducing a lot of extra baggage, right? So like I said, we don't really care about the stuff up here, right? Indeed, the phase should really be a property of the ground state. And I guess one way to see that, okay, just very briefly, one perspective that makes that clear is if there is a path in the parameter space that goes from A to A prime without closing the gap, it means that there's a unitary transformation that we can get by just the adiabatic evolution from here to here that takes us from this ground state to another. Okay, maybe you need to do a little bit better than that, but it means that there's a circuit. There's a collection of quantum gates that acting on this ground state produces this ground state. And the fact that you can do this without the gap closing means that it can be adiabatic without taking forever, without taking a time that grows with the system size. So there's a circuit that produces this ground state from this ground state with a depth that goes like the system size to the 0th power. So that's a point of view which would allow us to define phases without making reference to the Hamiltonian. Okay, but I'm trying to be kind of condensed mattery. So that's part of the reason why I wanted to talk about the Hamiltonian. Okay, good. Right. So this. Oh, yes, please. Thank you. I don't. Yeah. So right. So I guess So maybe here's the point of view. Suppose I have some. Yes. Good. So the question was, I said I wanted to. My equivalence relation is stronger than just adiabatic evolution, and you might be bothered by the fact that this changes the dimension of the Hilbert space. Yeah. So indeed, this space is not just the space of Hamiltonians on a fixed Hilbert space because of that. It's a slightly scarier thing. But the thing that I'm trying to build in there is, suppose I have some wonderful quantum state that represents your favorite phase of matter. There it is. It's some representation of it. And then someone comes along and just sticks an extra qubit here that's not doing anything. It doesn't participate in this. The symmetries don't act on it. It's not coupled to anything. It doesn't do anything at all. Clearly we should regard these as being in the same phase, right? Or even, okay, here's a really condensed matter answer to this question. In any material, people, the thing that people talk about when describing what state of matter it is like the valence electrons, right? So that there's a bunch of atoms. They have valence electrons, which are the ones that can get taken away from the atom and do something interesting. But those atoms have lots of other electrons in there, right? There's all these core electrons that don't do anything at all, right? So that's like what these things are doing. If I make some phase of matter with one material that has some number of core electrons and make this, make the same state with another material that has different core electrons, like, more of them, clearly that we should regard these as the same phase of matter. So that's what I'm trying to build in by this stronger equivalence relation. Does that make sense? Okay. Okay. So here's an example of this mythical integer that can distinguish between these things. Yeah.
Is there an analogous classification or definition with Euclidean lattice model?
The question was, yes, is there an analogous definition for Euclidean lattice models? Okay, and the reason I remembered to answer this question because I don't know the answer. The reason I remember to repeat the question is because I don't know the answer. Well, I mean, I guess, yeah, we do speak about phases of matter for at finite temperature, right? So a special case of, okay, yeah. So right here I'm talking about zero temperature physics, right? People do speak about phases of matter at finite temperature, which is also interesting. I kind of ruled that out by the third word in my title. But indeed, right, so at least for special Euclidean systems where we think of the measure as e to the minus beta h with some local h, indeed, I guess people do have such a classification. I mean, you could try to make such a classification, but I don't have much to say about it. It's indeed.
Sit on the line and there's a phase transition, move off the line and you ask if the phase transition persists.
Indeed, certainly, how to say, one can define phases of matter at finite temperature. I just don't want to talk about it. Yeah, indeed. Good, and actually many similar. So you'll notice that I made a somewhat I did a sneaky thing, which is I only defined gapped phases. But even in the introductory words that I said a few minutes ago, I said something about phases with gapless degrees of freedom everywhere in the phase. And so I haven't even told you what I mean by a phase more generally. And so I guess maybe I should say, so in that case, we can't talk about the wall of gap closing since the gap is already closed. And then I have to resort to the definition that people usually use, which is just that something bad happens. That is a phase transition, right? Two states are distinct if something bad has to happen in between. Or by bad, I mean something non-analytic as a function of the parameters. Okay. All right. So good. So finally, here's an example of a topological distinction. Yeah. So this word topological. Here's the first place where it's appearing. A quantity is topological if it can't change under smooth deformations, right? So this mythological integer, which is the same for A and A prime and different for B, is an example of a topological quantity. One reason that something could be topological if it has to be an integer, if there's a gap. Here's an example. So over there, we introduce this parameter R, describing the distinction between this potential and that potential. And there's a critical value of R. Oh, you know what? Let's talk. Okay, here I talked about the U1 case. Let's talk about the Z2 case instead, right? Let's talk about the Z2 case instead because it's easier to draw. So if R is positive, the potential looks like this. If R is negative, it looks like this. The symmetry acts like this. And there's a sharp transition between these. And one way to know that there has to be a sharp transition no matter what you do is that here, the number of ground states is equal to 1. And here, the number of ground states is equal to 2. So the number of ground states, whatever you say about it, one nice property that it has is that it's an integer. If the system has a gap, there's some integer number of ground states. And so we know that for sure, whatever you do in between, whatever other parameters you vary, there has to be a sharp distinction between these two things. Okay, so far the only example of a topological distinction I've given you is for this these sort of traditional phases, which we understand as being distinguished by symmetries. So in this sense, even those phases of matter are topological. nevertheless, people usually reserve the name topological phases for phases of matter that are distinguished by something other than symmetry breaking. And there's two. It's worth dividing them into two classes: those without topological order, and those with topological order. And now I will define what I mean by topological order. I guess there are many ways to define it, but maybe a good one is a state has topological order if it has excitations that can't be created by any local operator. So let's unpack that definition. It has excitations that can't be created by any local operator. If you think about this definition a little bit, you'll see that it's consistent with Meng's discussion of punctures. So in the special case of 2 + 1 dimensions, such a thing is a particle. And if it's not created by any local operator, it has to be created by some extended operator. So the idea is that the excitation itself is a particle, but it inevitably has something attached to it. So okay, so here's the excitation, but the operator that creates it is supported instead on some higher dimensional thing like a string, like an open string. And yeah, so in that case, they're called anyons. And a consequence of the fact that they're not created by any local operator is that their quantum numbers can be basically whatever they want, right? In particular, they can have fractional statistics, and they can have fractional charges. Let's think about fractional charges. So, this whole thing is neutral, but this end can have, some charge a third, and this end can have charge minus a third. And so, yeah, so it's because of the fact that they're not created by local operators that they can have interesting quantum numbers. Okay, so yeah, you've already heard a lot about the mathematical theory of anyons, so maybe I won't say too much about it. But there's one implication of this fact is that I guess maybe let me not be too okay. A symptom of this phenomenon is that the ground state degeneracy, the number of states below the gap there, depends on the topology of space. Ground state degeneracy depends on the topology of space. So for example, on a sphere, there's a unique vacuum, but if you put the thing on a torus, there can be multiple vacua. And the idea is that the multiple vacua are related to each other. So here's one ground state on the torus, are related to each other by the action of, here, let me draw it in yellow just to emphasize that it's the same thing, by the action of these operators that transport the anyons. So it's not a, if I were feeling brave, I would write an implication sign from there to there. So this is the idea. So depending on, for example, if there are these kinds of topological particle excitations, the number of ground states will depend on the number of non-contractible cycles of the manifold you put the thing on. And one nice consequence of this mechanism of producing a ground state degeneracy is that these states are related not by any local operator. They're related by these extended operators. Yes, please. Yeah, that's right. So the red X is meant to be an excited state. So here there's no red X. Yeah, so the idea is, think about this thing as the result of producing a pair of anyons, dragging one of them around the cycle of the torus, and then annihilating them again. So at the beginning and the end, there's no anyons. So it's a map from ground states to ground states. Yeah, good. Thank you for the question. I forgot to repeat the question.
More or less.
Okay. All right. Okay. So right, I was saying because of the fact that oh, sorry. What do I mean by this? Sorry. Sorry. I wrote a nonsense. Here. This is. So this is the ground state without anything, and then there's some operator, which I don't know. Let me call it W, which lives on this curve, which produces one ground state from the other one. And because they're related by a non-local operator rather than a local operator, this ground state degeneracy is robust. So that is, if I make a small perturbation of my local Hamiltonian, that perturbation, it can never go from here to here. It takes an infinite order in perturbation theory in the thermodynamic limit to get from here to here, and so the ground state degeneracy is stable. Okay, so then, so maybe, let me just add that adjective, robust ground state degeneracy. There's a third symptom of topological order that, if this were a different lecture series, I would emphasize much more, which is that they have long-range entanglement. So I guess maybe you can already see that from the definition. So I said that, suppose A represents a product state, right? So that's, I'm willing to call that representative of the trivial phase. So any representative of the trivial phase I can get to by acting with a finite depth circuit on a product state. But the fact that this is a different phase, that is necessarily separated from those states by some wall of gaplessness, means that I must not be able to do that. I must not be able to make this ground state by acting on a product state with a finite depth circuit. And so that's, in that sense, it has an amount of entanglement that you can't make just by acting with a finite depth circuit. Yeah.
When you say finite, you're talking about the size of the system.
Exactly. Yes, by finite I mean L to the 0. Exactly. Yeah, finite in the thermodynamic limit. Great. Okay, so I'm not going to emphasize that part. Okay, there's an interesting special case of topological phases with topological order, which is fractons. Maybe I'll just say a few words about that here. Has anybody talked about fractons in this school so far? You talked about it. Okay, all right. Okay, so maybe I'll say a little more about it then. Which is, I said topological order means it has excitations that can't be created by any local operators. Let me define fractons as it has excitations that not only can't be created, but they can't be moved by local operators. Perhaps in just some directions rather than other. Yeah, maybe. Well, let's allow ourselves perhaps in some directions. So this is strictly stronger because obviously if I could create them by a local operator, I could just annihilate them here and then create them over here. But okay. So this is a special case here. Okay, so now I think maybe that's enough vague, big words, and let me try to be a little more concrete. So Meng in his lectures gave, he throughout his lectures he used this example of the quantum double model, right? Actually I was really amazed by how simple he made it seem, because I usually think of the quantum double model as this complicated thing. And it is a complicated thing relative to the model I want to spend a few minutes talking about, which is the toric code. So has anybody written down the toric code Hamiltonian in the last month? Someone did? Well, he wrote down the quantum double Hamiltonian, which is, of which this is the special case where he said the group to Z2. Right, so in that sense he did, but I think perhaps a little more concrete might be helpful. Let me just say a few things about it. Okay, so let's put some qubits on the links of some graph. Right, so qubits on the links of a graph, and I guess we really need a little bit more structure. We need to know some choice of what we regard as plaquettes of the graph, as two cells of the graph. And but just from that information, we can write the toric code Hamiltonian as a sum over, let's write the plaquette term first, plaquettes of z, 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 z around the plaquettes, where z means sigma z, acting on the indicated qubit. Let's put a minus sign. And a sum over vertices of x, 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 where x means sigma x. And I've written it for this as if I'm talking about the square lattice, but actually nothing I'll say depends on that. So I guess maybe if I want to be a little more general, I guess really here it's some cell complex, and I'm putting the qubits on the 1 cells, and here this thing is the boundary of a 2 cell. This is a sum over 2 cells, and this is the boundary of the 2 cell, and this is the sum over 0 cells, and this is the adjoint of the boundary map. Okay, but anyway, you can just think about the square lattice if you want. And so these terms all commute. And I guess part of what I want to emphasize is that this is, it's not too crazy of a spin Hamiltonian, right? So qubits on the links of some, say, the square lattice, that's a collection of degrees of freedom you could imagine arising in some real physical system. And this Hamiltonian, well, it's not 2-body interactions, but it's only 4-body interactions. It's not too crazy. And I guess actually now there is a sense in which this model exists in nature. Well, depending on what you call, maybe nature is not the right word. It exists, there's a sense in which it exists in the sense that people have made it in artificial condensed matter actually in several ways, in cold atoms trapped in optical lattices, and in ions trapped in whatever they trap ions in. There's some, and also on this Google quantum computing chip, they've made this model. So okay, so it exists. Let's talk about it. Here's a useful notation, which will bring out the generalized symmetry structure. I'd like to let's denote. I'm going to pick a basis for the Hilbert space, where on each link there's 2 states. I'm going to think about the state where x equals 1. I'm going to draw that as nothing, and if x is minus 1, I'll draw that as I'll draw a link there. And let's write the ground state in this basis. So because the terms all commute, we can diagonalize them individually. What are the eigenstates of this operator? Well, in this notation here, the ground states, we want eigenstates of this operator with eigenvalue +1, right, to lower this energy. So okay, if there's nothing at all, that's an eigenstate with eigenvalue +1. If there's a string like that, or a string like that, this is +1, this is +1. If there's something like this, it's -1, right? And if there's something like this, it's -1. So okay, so what do these have in common? The ones that are bad are the ones where a string ends, right? So I'm gonna call this a string, and the terms that make the star term happy are the ones where the string proceeds happily through the. Here, so this one is also +1, where the string proceeds happily through the vertex, make the star term happy. The ones where a string ends makes the star term sad, right? Okay, so that says that the ground state of the star terms is superpositions of closed strings in this notation, right? So then, let's call this A. I don't know, A sub star, and this is B sub square. So A star equals 1 says that the wave function is a sum of closed strings. Let's just call C is the state of the closed strings. So if I had more energy, I would draw some configuration of closed strings inside the ket. It's a nice application of Dirac's wonderful notation. You can put whatever you want inside the box. And now let's diagonalize the plaquette operator. So how does BP act on a given state. Well, how does BP act? Suppose I draw the lattice really lightly. Suppose there's no strings at all. What is and this is P. This is the plaquette. What does it do? Well, X and Z anti-commute, right? That's really the only relation I'm using here. Right? That's also why these things commute. And so if I act with this product of Z's on a plaquette on a state where all of these X's is 1, what do I get? Yeah, I get a closed string on the boundary of that plaquette, right? So this thing is a creation operator for a closed string on the boundary of the plaquette. It's also an annihilation operator. If I start with this state, I get back to this state. And more generally, BP acting on this curve C is C plus the boundary of P. So we're by this notation. What I mean is, C is some collection of closed strings. Here I'm adding to that collection the boundary of the plaquette P, mod 2. Right? It's mod 2 because of this fact. And so the condition that BP equals 1 on our ground state for all P, it says that this wave function, psi of C here, has to be the same for any two configurations. Well, first of all, if they're related by adding a single plaquette, but by repeatedly adding plaquettes, we have to get the same wave function for any two closed curves that are in the same homology class. If they differ by adding a collection of boundaries of plaquettes. Okay, so what we've learned is that the ground states of this simple model are precisely correspond to the ground states of the Tor code are the first homology. That's the lower one, yes. First homology of the spatial manifold with Z2 coefficients. The Z2 is just because of this mod 2 business. And M is this is on M. M is space. Okay. So if, in particular, if we're studying the system on a simply connected thing like a sphere, there's a unique ground state, which is so on a sphere, there's a unique ground state, which is, now I really will draw the loop, superposition of loops. So if you like, this is we are witnessing the phenomenon of string condensation, right? So particle condensation happens when, that means that the operator that creates the particles has an expectation value, right? So a state where particles are condensed is a superposition of different numbers of particles. Here, the state that creates the strings has an expectation value, this BP, and therefore the ground state is a superposition of states with different numbers of strings. Okay, there's a unique ground state. But if we put the thing on a torus, then this relation no longer completely specifies the wave function, because the wave function in sectors where the strings wind around the cycles of the torus are not related to each other by this local condition. Instead, this is the equation that I was mumbling about over here. In this example, I can make it very precise. Instead, they're related by that equation, where W, well, let me call W sub C, is a product over links in the curve C of Z's. Z is in the link. This operator commutes with the Hamiltonian. In fact, the plaquette operator in the Hamiltonian is just one of these for the case where the curve is the boundary of a single plaquette. So we can make a collection of ground states. Yeah, so this is just the same equation I wrote before. This is Wx acting on this state, which is just, this, I should say what this state is. By this state, I mean exactly this. The sum, this is equal to the sum of contractible curves. Contractible closed curves. Okay, and there's another one where we go this way. And then there's one where we go both ways. Okay, and these states can be distinguished from each other. I can prove to you that they're orthogonal by operators I'll call V, and let's call it C check, which is a product over links that are perpendicular to C check. C check here is this curve in the dual lattice. Here I'm specifying to the case of 2 dimensions when I say that it's a curve of x sub L. And these these operators, these two operators, here's a picture of space. These guys are yellow. If here's a W and here's a V, we can ask about what happens if I move a W through a V, and I claim the answer is a -1 times the intersection number of the 2 curves. Yeah, I guess maybe to be more precise, the V is really something like this. That's what I mean by perpendicular to, and the W is really like this. And if I drew this more clearly, there would be a single link where they cross, and the X on that link and the Z on that link anti-commute with each other, and so that's where this minus sign comes from. Okay, so these operators form a Heisenberg algebra if they intersect, and V's also commute with the Hamiltonian. I should have said that too. And the star operator is the V along the star operator is V around that curve in the dual lattice. And they both commute with the Hamiltonian, but they don't commute with each other. So the ground states have to represent this algebra, and so therefore there can't be a unique ground state. And the bases I've chosen, I think, are eigenstates of V, are related to each other by the actions of W's. Okay, so those are closed string operators, right? So on a torus, we can choose these things to be non-trivial, non-contractible closed curves. And based on what I said here, you might anticipate that if we don't close the strings, that they'll create interesting excitations. And indeed they do. What time am I supposed to stop? Okay. Okay. So let's ask what happens if I, okay, there are 2 types of excitations. One of them is if I act on this, on a ground state with W of a curve that's, here, let me just draw it like this. Of a curve that has a boundary, then this creates what we'll call E particles at those places. And if I act with V on a curve that, I shouldn't have used red there. Let's make it purple. On such an open curve, we get these particles that are called M. And because of the, so E and M are each individually just ordinary bosonic particles. It seems like I'm not fulfilling my my claim that these things will have interesting statistics. The interesting thing comes from this fact. It comes from the fact that the creation operators for the E particles and the creation operator for the M particles fail to commute with each other. That fact implies that E and M are mutual semions, meaning that there's they pick up a minus one if you move one of them around the other. And another consequence of that is their bound state, let's call it EM, is a fermion. So the fact that there's a fermion in this system, so this is something that you can check by using the definition of fermion, right? So fermion means if I have 2 of them and I exchange them, I pick up a minus sign. And so you can check that minus sign comes from this minus sign. And the fact that there's a fermion, maybe you don't think it's a big deal, right? An electron is a fermion, and there's fermions all over the place. But this model started with a Hilbert space, which is a tensor product. Right? It's a tensor product of just qubits on the links of this lattice. And there can't possibly be a neutral fermionic excitation, exactly for because of the distinction that Schuhing was making at the end of his lecture today, that in a bosonic Hilbert space, there can't be any neutral fermions. That's what distinguishes the Ising model from the Majorana CFT. And indeed, there can't be here either. But that's OK, because the thing that I'm saying is a fermion is it's not created by a local operator. It always has this string attached to it. OK, so I think so many of these things, of the things I've just said, are follow from things that Meng said in a more elegant way, and a more elegant and more general way. But one thing that I wanted to emphasize here is that this Hamiltonian that I wrote, it's a very special Hamiltonian, right? Clearly, it's very special, but it's a representative of a phase of matter. So although that Hamiltonian is special, it's actually it's a special representative of a phase of matter, but it's nevertheless a representative. It's a fixed point. Is a fixed point, which represents a bigger phase of matter, which let's think about this case. Let's think about sum over links. We can add x, and we can add z. Right, so clearly, I'm not assuming any symmetries of my Hamiltonian at all. So really, I can't prevent you from adding these terms to the Hamiltonian. And what happens if you add them? Well, there's a by now very precisely known answer. But one thing that you know right away, I shouldn't say you know right away because Matt Hastings spent a long time proving it. But the fact that these degenerate ground states are related by non-local operators means that if I perturb the Hamiltonian by a local perturbation, like this one, the ground state degeneracy has to survive in an open set in the parameter space. So maybe let me first explain a little bit about why it's true, and then I'll draw the picture. So think about, here we go. Think about doing perturbation theory. Let's just pick one of them. Let's do perturbation theory in X. So we want to do perturbation theory in this XL. There's some coefficient H here. And in order to split the degeneracy, we need to go from this state, the state where there's no loops, to this state, the state where there's a loop. Right, and what's the loop? The loop is a product of, well, it's a product of x's, right, on this curve. And I'm drawing this, representing this torus as a little square, but you should think of the torus as a really big square. Right? We're interested in the thermodynamic limit, where this size of the torus is L. And think about perturbation theory. Right? We want to, in perturbation theory, we pull down powers of this interaction. And by pulling down powers of that interaction, I have to get from here to here. Right? So at each order in perturbation theory, I only pull down a single x. Right? There's a sum over which one it is, but there's just one power of x. Right? So in order to get from here to here, I have to act with one x, I have to act with another x, I have to act with system size worth of x's. And each one costs an order in perturbation theory. And there's some factor of whatever so at the intermediate steps I go off shell, there's some power of that energy cost, which is when I add an x, I violate the Plaquette operator. I should have given a name to the coefficient of the Plaquette operator. Anyway, the denominator is the power of that. This is in units of the Plaquette operator. And so this is equal to, so this is the splitting in perturbation theory. And so this is equal to g to the L, where g is, h. H is this perturbation, which, let me rewrite that as e to the minus L log h to emphasize that it decays exponentially with the system size. Right? So the split, so in perturbation theory about this special point, the degeneracy it survives exponentially well, even in finite size. And in infinite size, it just totally survives. And so the phase diagram looks something like this, where in here is this phase with topological order, the deconfined phase. And obviously, if I make this coefficient big enough, right, if I make h bigger than any other scale, we'll just get the ground state of XL, which is just every spin points to the right. It's just a product state, right? So this is just the trivial phase. An aspect of this that I haven't emphasized is the connection to gauge theory. In terms of the gauge theory, I guess we would call, let's see, one of them is the Higgs phase. I think this is the Higgs phase, and this one is the confining phase. But they're really the same, right? Because this is just the product in the x basis. This is the product in the z basis. We can just rotate from one to the other. OK. So I've emphasized the toric code, the Z2 toric code on the square lattice. As you already know from Meng, there's many possible generalizations. We can replace Z2 with an arbitrary finite group. In the case where the degrees of freedom are abelian, right? If we only replace Z2 with Zn, we could instead place the degrees of freedom on the p cells of our cell complex rather than the 1 cells. In that case, instead of computing the first homology, we'll compute the pth homology. OK, we can twist by cocycles, by modifying the plaquette operator or the star operator, and get this kind of Dijkgraaf-Witten theory. Let's see, are there any other generalizations I wanted to mention? OK, maybe not. All right, questions about the toric code? Yes?
Is there a way to chart the difference between the combining and phases?
No. Oh, yeah, indeed. If there were some extra symmetry that we cared about, you could maybe make some distinctions. The question was whether under some circumstances, like if we care about some extra symmetry, there are sharp distinctions between the Higgs phase and the confining phase. And then yes, I'm sure there is. Yes, in particular, actually, there's some interesting story about higher form symmetry in that regard. But I don't have more to say about that right now. Okay, so this was one example of sort of paradigmatic topological phase, a phase that's distinguished from the trivial phase by something other than symmetries. I feel a little guilty about talking about this as a sort of representative of condensed matter, because, like I said, it's only been found in artificial condensed matter. So maybe to help allay my guilt, let me spend the remaining time today talking about quantum Hall states. And I'm going to I'm not going to start from a microscopic description. I'm going to instead give a sort of effective field theory perspective on quantum Hall states, but from which we can understand how they're different, and from which later we'll understand their symmetries. So what's a quantum Hall state? It's something that happens generally time reversal. Well, generally time reversal is broken because one signature of it is the Hall conductivity, which is 0 if it's time reversal invariant. The Hall conductivity takes some rational values, and it happens in 2 + 1 dimensions, and it's something that happens to electrons. So just from this information, let me write down an effective field theory for it, which is, so there's a conserved current. Let's call it J. And we're in 2 + 1D, and no time reversal. So those are the inputs. And so the fact that we're in 2 + 1 dimensions means that I can solve this equation. Okay, you guys are high energy physicists. I should be careful about my up and down. No, okay, wait, yeah, sorry, it's fine. And let me put 1/4π, 2π. Okay, so if A is single valued, this is a solution of this equation, right? You agree? Just like think about E and M, right? If I have a divergence-free vector field, that means it's the curl of something. So these A's are my degrees of freedom, and they're gauge fields, because you see if I replace A by A plus A by A plus G inverse dg, I get back, it doesn't change J. What can the effective action be? Actually, more generally, I guess if I want to be more general, there could be more than one of these guys. Sum over I. And so it's the effective action for a gauge field in 2 + 1 dimensions with no time reversal symmetry. So you could write a Maxwell term. But because of the fact that there's no time reversal symmetry, there's another term that you can write, which is a Chern-Simons term. And compared to the Maxwell term, the Chern-Simons term is more relevant, right? The gauge field has dimension 1, so this is marginal, and this is an irrelevant operator. So that's it. That's the whole story. Well, so from here we can derive the consequences of it. It's a topological field theory if I don't include the Maxwell term, because, well, I wrote it down without even introducing the metric, so correlation functions of A can't depend on distances. The equations of motion, in the absence of matter, just say that A is flat. So there's no local gauge invariant degrees of freedom. And right, so that's if we ignore the Maxwell term. With the Maxwell term, there is a local degree of freedom. It does require the metric, but it's massive, right? So yeah, with the Maxwell term, it's a fun exercise to show that the equations of motion instead say, let's write it this way. What did I called it 1 over g squared. Instead of 1 over g squared, let me call it 1 over 4m squared, where m is a mass scale, to emphasize the fact that it's irrelevant. This is minus mk over 2 pi all squared, acting on f mu. So f in the presence of the Maxwell term satisfies a massive wave equation, where the mass is given by the scale in which the Maxwell term appears. So if you set the Maxwell term to 0, that mass goes off to infinity, and we can forget about all the local degrees of freedom. Okay, if I really demand this gauge invariance, impose this gauge invariance, it implies, including under large gauge transformations, including like if I put the system on a torus, including configurations of G that wind around the torus, it imposes that K, it's a symmetric matrix, because this thing is symmetric, its entries are integers. Okay, it's a symmetric matrix of integers, and yeah. So to see that, so I wrote this down from very general principles, but to see that it has something to do with quantum Hall physics, there are a few ways to do that. The first thing we can do is include the coupling to, so we have this conserved current J, so we can couple it to a background field. In the case where the current is the current of electrons, that background field is just the electromagnetic field, but we're not going to think about dynamics of the electromagnetic field. We're just going to think about it as a background field. And one reason to do that is to ask about the quantum Hall response. The Hall conductivity is just the second derivative with respect to that background field of the effective action. So that is, so A is this background electromagnetic field. That couples to the system through this current J, which is written in terms of our gauge fields like that. And let me just write it as ADA. And now if we compute the effective action for A upon integrating out little a, so this includes the Chern-Simons term and this coupling to the background field, we get something that's quadratic, right? It's just a Gaussian integral. And its coefficient is sigma xy. And we learn that sigma xy is e squared over h times t k inverse t. So t are these entries in this charge vector, which has to be quantized for the charge to be quantized, and k is just the inverse of this integer matrix. So in the simplest case, so for example, let's take the case where k is just a single number and t is just 1. This says that the Hall conductivity is e squared over h times 1 over k. So, which is, for example, that's what happens in the Laughlin state, where k is 3. And from this point of view, we can also understand the anyons. So the description where we throw away all this other stuff, it doesn't have dynamical particle excitations. The idea being just that they're heavy, right? It's a description of the stuff below the gap, but we can include them as test particles, and there's a very simple way to include them. Include quasi-particles. They're just charges that are minimally coupled to our Chern-Simons gauge fields. So let's call it this guy. It's just integral AI of some background current, some external current of quasi-particles. For example, we can take the current to be a delta function, right? That describes a single particle sitting still. Well, a few simple things. One is if they have fractional charge. If we combine this term and this term, we learn that the equation of motion say, so in the presence of this term, the equation of motion, rather than saying that the gauge field is flat, the gauge field is attached, the flux is attached to the charge. All right, so yeah, this is called flux attachment. Right, the flux should be a delta function where the charge is. And then if I use the equation of motion for the other bits, we learn, using the form of J, that says that the density, this is the actual electromagnetic charge density, is E fxy over 2 pi is E over k in this example. All right, so that says that one of these quasi-particles has electric charge 1 over k. And moreover, they have fractional statistics. Great. I think maybe by then I'll have said most of what I wanted to say about fractional. Okay. They have fractional statistics, which maybe it's already clear. So because the charge gets flux attached to it, if I have two of them, each of them has magnetic flux attached to it. And so when I move one of them around the other, the charge here sees the flux here, and there's an arrow in a both phase. All right. Delta phi 1, 2 is Q1 integral over this curve of A, which is Q1 integral of B. By B, I mean this F. I guess I should call it F. Over this region, R, whose boundary is C, which is Q1 2 pi over K Q2. So that's the phase you get by moving one of them around the other. And you can see that if Q1 and Q2 are integers, this is a fraction. And then the final thing, which we get from this very simple, very crude, very, very low input description of quantum Hall phases, is we can ask what happens if we put them on a space with boundary. And I guess this is the last thing for today, which is, so we said that there's this gauge redundancy of shifting A by an exact form, but the Chern-Simons term, as I think you probably have seen, is not invariant under that transformation if space has a boundary. So let's suppose we have a quantum Hall fluid in the lower half plane, and let's think about let's think about just the simplest case of the Laughlin state. Under A goes to A plus d phi, this is this integral over the lower half plane. This is not invariant. It goes to S plus some something that's not. Oh, sorry. Yeah, let's. Okay, let's just say it's not invariant. Well, what does that mean? So there are two ways to look at it. One is, well, that means that this transformation must not be a redundancy. It must not be an equivalence between two different configurations. And so that should mean that A goes to A plus d phi with phi on the boundary non-zero is not a redundancy, but rather a symmetry. Redundancy. Another perspective is, well, we could demand that it's a redundancy, but then we have to add some degrees of freedom on the boundary to cancel this non-invariance of the action. So I kind of like this perspective better, since the degree of freedom we have to add is exactly phi on the boundary. So you can't stop me from adding a term on the boundary, which looks like this in that case, which is a sub x squared times some coefficient, which I'll give a name here. Since if this transformation is we're no longer demanding that it's an equivalence, this thing is gauge invariant. And so then let's look at the equations of motion. So the equations of motion say that that f is 0. Well, that says that A is d phi, which looks like it's trivial, but if phi is not 0 at the boundary, we declare that that wasn't an equivalence anymore. And so if we evaluate the Chern-Simons action on this configuration, what we get after a bit of calculation, including this boundary term, is this action. dt phi dx phi from the Chern-Simons term plus v dx phi squared. Which, well, it's not very Lorentz invariant, but what do you expect? But at the cost of a little bit of Lorentz invariance, it's an action for a chiral boson. Right? So you see the equation of motion are solved by if phi satisfies this chiral propagation equation. So what we learn is that there are modes on the boundary that move in only one direction. I'm sure I got the sign wrong, but they move in only one direction. And so maybe you know that this is not something that you can get from a local lattice model that lives just on the boundary, because any such local lattice model would have some dispersion relation, which, whatever it is, it's periodic with k. And so wherever the chemical potential is, it crosses the Fermi level an even number of times. We always get the same number of right movers as left movers. And by the magic of adding an extra dimension, we found in this way just a right mover. Or I guess it's just a left mover if v is positive. Okay, so I don't know. Maybe some of you have heard this story before, but if you haven't, I felt like it was a good use of 15 minutes, since quite a lot of physics comes out of very little input. Okay, so just to sum up, I've told you some examples in a little bit of detail of phases of matter that seem to go beyond Landau theory, and next time I'll tell you how they can be understood by generalizing Landau theory. Okay, thanks.
Maybe we have time for one question before lunch.
Say again? What sets the sign of V? Ah, great.
Could you repeat the question?
Yeah, the question is, what sets the sign of V? And there is, you can see from this term in the action Actually, KV has to be positive for stability. If KV is negative, I mean, it's KV because I called that combination KV. But if KV is negative, this term encourages wiggly configurations. So yeah, so indeed, it's K. It's the sign of the sign of the Hall conductivity that determines the sign of the velocity. Yeah, great.
Okay, before we go to lunch, let me just remind you all, I haven't mentioned this, but you probably are aware that John is giving, in addition to his lectures to all of us, a public lecture, not today, but tomorrow night at 7:30. It's going to be right downstairs. So the general public is invited. This will be at a slightly lower level than what's delivered to Tassie, at least, that's the intention. But you're all welcome and encouraged to come. So that's tomorrow night downstairs, 7:30 is John's public lecture. So let's thank John for his nice talk again.